All right, welcome back to the deep dive. Today we're going really small, like really, really small.
Smaller than small.
Yeah, we're diving into quantum mechanics,
The subatomic world. The rule book for how things work down there.
which is,
Down where?
yeah,
At the most fundamental levels of the universe.
right. And it's a world where, well, a lot of our everyday intuition kind of breaks down.
It's a place of mind-bending paradoxes and some really revolutionary science. That's where quantum mechanics comes in.
Yeah, it's not just a new set of equations, it's like a whole new way of looking at reality.
A fundamental shift in our understanding of the universe.
So this all really started to emerge in the early 20th century, right?
Right. Physicists were hitting a wall. They had this beautiful framework of classical physics.
Which worked great for like planets and apples falling from trees, big stuff.
Exactly, the macroscopic world. But when they started peering into the atom, things got weird.
Yeah, I remember reading about this. Like, classical physics just couldn't explain certain things.
Right? Like the way light interacts with matter, or why atoms are stable in the first place. Why don't electrons just spiral into the nucleus?
Which they should, right, according to those classical laws.
Exactly. So there was this growing sense that something was missing, some deeper, more fundamental set of rules governing this subatomic realm,
And so quantum mechanics was born.
with figures like Max Planck, Werner Heisenberg, Erwin Schrödinger, and Niels Bohr leading the way.
It's pretty amazing to think about this huge shift in thinking all happening within a few decades.
A real scientific revolution. And it all stemmed from the realization that the laws governing the very small are fundamentally different from those that govern the large.
So are you saying there's like a hard line, like this is where classical physics stops working and quantum mechanics takes over?
Well, not exactly a hard line. It's more of a gradual transition. You see, quantum effects tend to become more pronounced at smaller scales, higher energies, and lower temperatures.
So the smaller you go, the weirder it gets.
Pretty much. In our everyday world, these quantum effects are usually averaged out, so classical physics works really well as an approximation. But those quantum phenomena are always lurking beneath the surface.
That's wild. Okay, so let's get into some of the specific weirdness, shall we? One concept that I always find fascinating is this idea of wave-particle duality.
Ah, yes, wave-particle duality. One of the cornerstones of quantum mechanics.
So what exactly does it mean for something to be both a wave and a particle? Those seem like pretty opposite concepts.
They do, don't they? In the classical world, we think of particles as these tiny localized objects like billiard balls.
Right, bouncing around.
And waves, on the other hand, are spread out disturbances like ripples on a pond.
Okay, so how can something be both?
That's the beauty of quantum mechanics. It embraces paradox. What wave-particle duality says is that fundamental entities like electrons or photons can exhibit properties of both particles and waves. It's not that they're switching back and forth, it's that they possess both natures simultaneously.
So it's not like a coin that's either heads or tails. It's like, I don't even know, a coin that's somehow both at the same time.
It's a difficult concept to grasp using our everyday intuition, but that's the reality at the quantum level.
Okay, so let's try to make this concrete. I know you mentioned light earlier. How does light exhibit this wave-particle duality?
Well, for centuries, we understood light as a wave. That's how we explained phenomena like diffraction and interference.
Like when light bends around corners or creates those rainbow patterns?
Exactly. But then, in the early 20th century, experiments like the photoelectric effect showed that light also interacts with matter as if it were made up of discrete packets of energy.
Like little bundles of light.
Right. These bundles, these quanta of light, are what we call photons, and that's the particle-like behavior of light.
So sometimes light acts like a wave, sometimes like a particle. How do we know which it's going to be?
It depends on how we observe it, on the experiment we perform. If we set up an experiment to look for wave-like properties, that's what we'll see. But if we set up an experiment to look for particle-like properties, that's what we'll observe.
So it's like light is showing us different faces depending on how we look at it.
In a way, yes.
Hmm.
It's a reminder that our observations are not passive. They actively shape the reality we perceive, especially at the quantum level.
That's pretty profound. Now, you also mentioned electrons earlier. They're typically thought of as particles, right?
Right, tiny little particles orbiting the nucleus of an atom.
So how do they exhibit wave-like behavior?
Well, there's a very famous experiment that demonstrates this beautifully. It's called the double slit experiment.
Ah, yes,
Uh.
the double slit experiment. And this is where things get really mind-boggling, right?
It is indeed. Imagine we have a beam of electrons, and we fire them at a barrier with two narrow slits in it. Behind the barrier, we have a screen that detects where the electrons land.
Okay, so if electrons are just particles, what would we expect to see on the screen?
Well, classically, we would expect to see two distinct bands of hits on the screen corresponding to the two slits. The electrons would go through one slit or the other, like tiny bullets.
Makes sense. So what actually happens?
Well, that's the amazing part. What we actually see is an interference pattern, a series of bright and dark bands, just like you would get with waves interfering with each other.
So the electrons are somehow interfering with themselves as if they're going through both slits at the same time.
That's the interpretation. It's as if each electron is behaving like a wave, spread out in space, and passing through both slits simultaneously. And then these waves interfere with each other, creating the interference pattern on the screen.
Okay, I think my head is starting to hurt, but it gets even weirder, right? Because if you try to actually observe which slit the electron goes through,
Then the interference pattern disappears. If we put a detector at one of the slits to see which way the electron goes, we suddenly get back the classical result, two distinct bands on the screen.
so the very act of observing, of trying to measure which path the electron takes, changes the outcome.
Exactly. It's as if the electron knows it's being watched and decides to act like a particle instead of a wave.
Like it's shy or something.
It's a deep mystery at the heart of quantum mechanics. The act of measurement, of interacting with the quantum system, seems to force it to choose a definite state.
So we can't even observe the wave-like behavior directly. It only shows up when we're not looking.
In a sense, yes. It's like trying to catch a glimpse of a fleeting shadow.
Yeah.
The moment you try to grasp it, it vanishes.
That's pretty frustrating. Is this something to do with our limitations, like our measuring devices aren't sensitive enough, or is it something more fundamental?
It's more fundamental than that. It's not a limitation of our technology. It's a fundamental principle of the universe itself.
And that principle is?
Heisenberg's uncertainty principle.
Oh, right. That's the one that says we can't know both the position and momentum of a particle with perfect accuracy, right?
Precisely. The more precisely we know one, the less precisely we can know the other.
So there's always some inherent fuzziness, some uncertainty in our knowledge of the quantum world.
Always. It's built into the fabric of reality itself. And this uncertainty isn't just a lack of knowledge, it's a statement about the very nature of the quantum world. The properties of particles don't have definite values until they are measured.
So before we measure them, they exist in this kind of blurry state.
In a way, yes. It's like they're in multiple states at once, a superposition of possibilities.
So what are some of the consequences of this uncertainty principle? Why should we care that there's this a fundamental limit to what we can know?
Well, for one thing, it explains why atoms are stable, why electrons don't just spiral into the nucleus.
Which they should, according to classical physics.
Right. But the uncertainty principle tells us that if an electron were confined to such a tiny space, its momentum would have to be incredibly large.
Meaning it would have a lot of energy.
And that energy creates a kind of barrier, preventing the electron from collapsing into the nucleus.
So the uncertainty principle is essential for the very existence of matter as we know it.
Absolutely. It's what keeps atoms from imploding.
That's pretty amazing. I remember reading about another consequence of the uncertainty principle, something called quantum tunneling.
Ah, yes, quantum tunneling.
Ah!
Another one of those mind-bending quantum phenomena.
So what is this quantum tunneling? Does it involve tiny shovels or something?
Not quite. Imagine you have a particle approaching an energy barrier. In classical physics, if the particle doesn't have enough energy to overcome the barrier, it just bounces back.
Like a ball hitting a wall.
Right. But in the quantum world, there's a chance, a non-zero probability, that the particle can actually tunnel through the barrier, even if it doesn't have enough energy to go over it.
So it's like the particle just disappears on one side and reappears on the other.
It's not quite that simple. It's more like the particle's wave function extends through the barrier, and there's a small probability that the particle can be found on the other side.
So it's like a ghost passing through a wall.
In a way, yes. It's a bizarre consequence of the uncertainty principle and the wave-like nature of particles. And it has real-world implications.
Okay, like what?
Well, for one thing, quantum tunneling is essential for nuclear fusion, the process that powers the sun.
So the sun wouldn't shine without quantum tunneling.
Not as we know it. The particles in the sun's core need to overcome a huge energy barrier to fuse together, and they do that thanks to quantum tunneling.
That's amazing. And I think I also read that quantum tunneling is used in some modern technologies.
Yes, indeed. It's used in devices like tunnel diodes and scanning tunneling microscopes, which allow us to image surfaces at the atomic level.
So this seemingly bizarre quantum phenomenon is actually quite useful.
It is, and it's a reminder that the strangeness of quantum mechanics often leads to remarkable technological advances.
Okay, so we've talked about wave-particle duality, the uncertainty principle, quantum tunneling. It's all very mind-bending. But there's another famous thought experiment that really highlights the weirdness of quantum mechanics, and that's Schrödinger's cat.
Ah, yes, Schrödinger's cat, a classic illustration of superposition and the challenges of applying quantum principles to the macroscopic world.
Before we get to the cat, can you remind us what superposition is again?
Superposition is the idea that a quantum system can exist in multiple states simultaneously until it is measured.
So it's not just that we don't know what state it's in, it's that it's actually in all those states at once.
Exactly. It's like a coin spinning in the air. It's neither heads nor tails until it lands.
Or like our electron going through both slits at the same time.
Precisely.
Hmm.
Superposition is a fundamental feature of the quantum world, and it leads to some very strange consequences.
Like Schrödinger's cat.
Right. So imagine we have a cat sealed inside a box. Along with the cat, we have a radioactive atom, a Geiger counter, and a vial of poison.
Okay, this doesn't sound good for the cat.
Well, that's the point. If the radioactive atom decays, the Geiger counter detects it and triggers a mechanism that releases the poison, killing the cat.
So it's like a deadly Rube Goldberg machine.
In a way, yes. Now here's the quantum twist. According to quantum mechanics, the radioactive atom is in a superposition of both decayed and undecayed states until we observe it.
Meaning it's both decayed and not decayed at the same time?
Exactly. And since the cat's fate is linked to the state of the atom, the cat is also in a superposition of both alive and dead states.
So the cat is both alive and dead inside the box. That's pretty disturbing.
It is. And that was Schrödinger's point. He wanted to highlight the absurdity of applying the rules of quantum mechanics, which work so well at the microscopic level, to macroscopic objects like cats.
So is Schrödinger saying that superposition doesn't apply to big things?
Not necessarily. The question is, where does the quantum world end and the classical world begin? How do these two realms interact?
And is it really the act of observation that collapses the superposition? Does it have to be a conscious observer?
Those are deep philosophical questions that physicists and philosophers are still debating today.
So is superposition just a theoretical concept, or does it have any practical applications?
It's far more than just theoretical. Superposition is the key to many emerging quantum technologies, like quantum computers.
Quantum computers, those are the ones that are supposed to be super powerful, right?
They have the potential to be. Quantum computers utilize quantum bits, or qubits. Unlike classical bits, which could be either 0 or 1, qubits can be in a superposition of both 0 and 1 at the same time.
So they can be in two states at once, just like our electron going through both slits.
Exactly. And this allows quantum computers to perform certain types of calculations exponentially faster than classical computers.
So this weirdness of superposition could actually lead to some pretty amazing technological breakthroughs.
It already is. And it's just the tip of the iceberg.
Yeah.
There's so much more we're still learning about the quantum world and its potential applications.
Speaking of learning, we also mentioned Niels Bohr earlier. What were some of his key contributions to this whole quantum mechanics story?
Niels Bohr was a giant in the field. He developed the Bohr model of the atom, which was a major step forward in understanding the structure of matter.
Remind us what the Bohr model is all about.
So before Bohr, there was the Rutherford model, which pictured the atom as a tiny solar system with electrons orbiting the nucleus like planets around the sun.
Which makes sense, right? But there was a problem with that model.
A big problem. According to classical physics, those orbiting electrons should constantly be losing energy, emitting radiation, and spiraling into the nucleus. But atoms are stable. They don't just collapse.
So what did Bohr do?
Bohr proposed that electrons can only exist in specific quantized energy levels or orbits around the nucleus. They can't just be anywhere. They're restricted to these discrete energy levels.
So it's like a staircase. The electrons can only be on certain steps, not in between.
A good analogy. And Bohr further proposed that when an electron jumps from a higher energy level to a lower one, it emits a photon of light, with a specific energy corresponding to the energy difference between the levels.
So that's why atoms emit light at very specific wavelengths, creating those unique spectral lines that we use to identify different elements.
Exactly. Bohr's model beautifully explained those spectral lines, something that classical physics couldn't account for. It was a major victory for the quantum
Mm.
approach.
So Bohr's model, with its quantized energy levels and jumps between them, really laid the foundation for our modern understanding of how atoms work.
It did. And it paved the way for the development of quantum chemistry, which applies quantum mechanics to understand the behavior of molecules in chemical reactions.
So quantum mechanics isn't just an abstract theory, it's at the heart of our understanding of chemistry and the very structure of matter.
Absolutely. And it's also the foundation for many of the technologies we rely on today.
Okay, so we've gone through a lot of the theoretical stuff, but let's talk about some real-world applications. Where do we actually see quantum mechanics in action in our everyday lives?
Well, you might be surprised to learn that quantum mechanics is all around us. It's not just confined to labs or research facilities.
Give me some examples.
Take lasers, for instance.
Mm.
Lasers work based on a quantum phenomenon called stimulated emission.
That's where one photon triggers the emission of another photon, creating that intense beam of light.
Exactly. And lasers are everywhere, from barcode scanners at the grocery store to fiber optic cables that carry internet traffic.
So we're using quantum mechanics every time we scan our groceries or browse the web?
In a way, yes. And what about medical imaging? Magnetic resonance imaging, or MRI, relies on another quantum phenomenon called nuclear magnetic resonance.
MRI, that's the one where you lie inside that big tube and it takes detailed pictures of your insides.
That's the one. MRI uses the quantum properties of atomic nuclei to create those images. It's a non-invasive way to diagnose a wide range of medical conditions.
So quantum mechanics is helping to save lives.
It is. And those are just two examples. There are countless other technologies that rely on quantum principles, from transistors in our computers to solar cells that convert sunlight into electricity.
So quantum mechanics is not just some abstract theory, it's the driving force behind many of the technologies that shape our modern world.
And it's still a young science, full of potential. We're just beginning to scratch the surface of what's possible.
So after this deep dive, what's the one key takeaway you'd like our listeners to remember? What's the most important thing to understand about quantum mechanics?
I think the most important thing is that quantum mechanics forces us to rethink our classical intuitions about reality. It tells us that the universe is not as deterministic as we thought, that there's an inherent uncertainty built into the fabric of the world.
So it's not just about learning new equations, it's about adopting a whole new way of thinking about the universe.
Exactly. And that new way of thinking has the potential to revolutionize not just our technology, but our understanding of who we are and our place in the cosmos.
Okay, and what's one final thought, one provocative question we can leave our listeners with to ponder?
How about this? If the very building blocks of reality, the atoms and particles that make up everything we see and touch, operate according to these bizarre quantum rules, what does that say about the nature of reality itself? Is the world we experience, with its solidity and predictability, just an emergent property of this underlying quantum weirdness?
Wow, that's a big question, and one that we'll probably be grappling with for a long time to come.
Indeed. But that's the beauty of science. It constantly challenges us to expand our horizons and to question our assumptions about the world.
Well said. Thanks for guiding us through this deep dive into the quantum world. It's a truly fascinating and mind-bending realm. Until next time, keep exploring and keep asking questions.